because we've got those, so might as well keep what it is. That notation. Okay. So if we solve this, we get our velocity of p prime right at the end of the elliptical orbit of being 70.7 or 70.5 rather times 10 to the third. Still got that there. Feet per second. Okay, so we've gone from a smaller orbit to a larger orbit, and we've decreased its speed. We were at 107, and now we're at 70.5, still 10 to the third feet per second. And what we need to do is we need to jump up, we need to fire a rocket so we increase our speed, then stay in the orbit of Mars rather than continuing our elliptical orbit, which would bring us out not where we want to go. So we can figure out that speed of the velocity of Mars, okay, exactly the same way we did here. It's this equation here, okay, g times the mass of the sun, which we already have, divided by this, in this case, the radius of Mars orbit, okay, square root of all that. So it's the same sort of thing that we got here. We're just changing the number down here to that 141.5 times 10 to the 6th. And when we do that, we get 79.2 times 10 to the third feet per second. Okay. And so the delta that we're looking for, okay, we need to increase from this speed here to this speed here. And so that turns out to be 8.66 times 10 to the third feet per second. Or if you convert that to miles per second, it's 1.640 miles per second. Which is comparable to what we did here at point A, 1.83, 1.64. And so, I mean, it's always nice when you're working with a bunch of large numbers that you end up with a comparable number what you started with. I mean, if this turned out to be 600 miles per second, and here we did 1.83 miles per second, your math is somewhere wrong. Okay, it's a good chance.
So how did you find out the velocity of V, just that first, the 79.2?
Yeah, so it's the same equation as this. Okay, all I did was put in here the radius of Mars.
Okay, gotcha.
Yeah, so I didn't write it out again.
Velocity of B.
So when at the very end, we use the angular momentum equation.
Well, what we used to go from A to B, was constant angular momentum, yes. Okay, so this would allow us to figure in the elliptical course, because we could figure out what we were in both circular orbits. Okay, that was this step in here. Okay. But between A and B, when we're in the elliptical orbit, because we're increasing R all the time. Okay, as we went from the smaller orbit to the larger orbit, R was slowly increasing. But what was staying constant was the angular momentum. Okay, so this is the value of the angular momentum. And we already talked about how the vector stays constant. Okay, direction of the vector stays constant. Okay, and so all we need to do is figure out that the magnitude stays constant.
And then is that where the relationship of where you were saying that as the radius is increasing, mass is staying the same, so the
Right, yeah, exactly. The mass is the same, so it's just the mass of the satellite.
Yeah.
We're going to a bigger orbit, so R is getting bigger, therefore the velocity has to go down, so that that whole product stays constant.
And then just one, when did we use this, the 32.2, this gravitational constant, the little to the left?
Yeah.
Right there, yeah. When did, where did that come?
That number?
Well, I know the number.
Okay, I know the number, okay. It came in this, when we
Alan will
knocked
not
out the
enjoy
surface
that.
of the earth, weight is equal to mass times little g,
Okay.
but that's due to gravity, so we can write gravity, the force of gravity, this law of gravity is true, this is the same thing as this, but when we're on the surface of the earth, we just say m times g. Okay, therefore that little g must be related to this.
Well, doesn't it come, don't they come from, I mean, isn't that where we get n times v?
Yeah.
V. Okay.
Yeah,
Okay.
so, I mean, if you look at it, g must be equal to this whole thing. Right. It's just, we don't write this out every time, okay? In general, the mass of the earth and the radius of the earth doesn't matter where you are, so it's always the same. Multiplied by the universal gravitational constant, and that's where we get the 32.2. Okay, it's just we know this number, so rather than figure out, use this big number in the mass of the earth, which we would have to look up somewhere, okay? We can just use G. Okay. But it only works on the surface of the earth, because that's where weight is equal to m times G. That's the only place that we use little g, is on the surface.
Right, but we use that to find out the other variables.
Right, yeah, so this is still true, because we made this relationship on the surface. Okay, but we can't say that this is true when we're out somewhere out here. Okay, it would be a different g, is what it would be.
Right.
Okay, it would be a different lowercase g. Okay, this is when we're on the surface of the earth, so this is the radius of the earth.
And then we can't, wouldn't we be, I mean, that g times mass of the earth, isn't that, I mean, isn't the mass of the earth something that we could, like?
We could have looked up it. Yeah, we could have looked up this, we could have looked up this.
Okay.
Yeah, I'm just showing that we can also figure it out this way. Okay. So, these relationships that we've been playing around with the last few days, dealing with space and gravity, you can manipulate them around for what you need, but you have to be a little bit careful with what we're talking about the radius. You know, if we're out in space, if we're talking the distance from the center of the planet to our satellite, or from the surface of the earth, okay, these R's change. So you have to be a little careful as you're going through this. Okay? And the other thing from this is, if we're dealing with a particle under a central force, then we can say this, that it's going to be constant. And the central force most of the time we're going to be dealing with is gravity. So, this is the last thing that we cover in this chapter 12. We covered a lot of stuff in chapter 12. But essentially what we've done in chapter 12 is say force equals mass times acceleration. Okay. We've done it in our x and y components, okay, but we've also done it in tangential and normal. Okay, in tangential and normal, then that's where we got our acceleration in the normal direction, and we proved that. Okay. But then we also looked at force equals mass times acceleration in transverse and radial, and that's where we got the theta dots and the r dots. Okay. And we'll use those as we go through the next few chapters as well. Okay. But again, the main thing for chapter 12, sum of the forces equals mass times acceleration. Okay. In whatever direction we're talking about. The x direction, the y direction, the radial direction, the tangential direction. Okay. And it's just those different unit vectors are useful in different problems. It'd be real nice if everything was just x and y.